In this video, I want to give you a short teaser for one of the more basic parts of the ILAB-X, the Internet Protocol and its newest version, IPv6. But what is the actual purpose of the Internet Protocol? By default, each network device has a unique address called MAC. These are assigned by the vendor of the device and usually do not change. Assume we have a scenario, as here, where two hosts are directly connected to each other. Host 1 could just send out messages with the MAC address of host 2 as destination, and host 2 would know the messages are meant for it when received. So far so good. We can address connected hosts via their MAC address. Why do we need another mechanisms, like the Internet Protocol? Let's extend our example. Now we have host 3, which is theoretically reachable by host 2 over another host in between. However, if host 1 sends a packet for host 3 to host 2 wouldn't know what to do with it and simply discard it. Why that? The answer is relatively simple. Host 2 does not know how to reach host 3 as it is not directly connected. Theoretically, each host could have a mapping of how to reach a certain host using his MAC and use that to implement multi-hop routing. However, MAC addresses are flat. That means they are not logically grouped by any mean that is useful for routing. Two MAC addresses that only differ in the last bit could be in opposite parts of the planet. Therefore, each host would need to store all possible MAC addresses and the next hop on the path to reach them. As MAC addresses are 48-bit long, hosts that want to store such a mapping would need 2 to the power of 48 bits of storage in the worst case, for MAC addresses alone. This corresponds to 256 terabytes of storage. This shows us that although global routing using MAC addresses is theoretically possible, it does not scale. The Internet Protocol solves that scalability issue. IP addresses are not randomly assigned but follow a certain pattern. The following example illustrates this. If host 2, which also serves as a router, receives an IP packet for host 3, it just has to look at the first few bits of the IP address to check where to send the packet next. So in this case, it would be 111.0.0.1, and then recognize, oh, that's in Australia, or basically a router in Australia, and forward it there. This is possible since IP addresses are assigned in certain blocks to different regions in the world, where MAC addresses are assigned almost randomly, depending on from which vendor you bought your network device. So in our case, a block starting with these bits could be located in Australia, but this is just an example. During the course, we will learn how IPv6 addresses look like, how they are structured, what different types of IPv6 addresses exist, and how they are automatically created and assigned to hosts. We also have a look at different types of IP addresses, supporting protocols, and the interaction between layer 2 MAC addresses and layer 3 IP addresses, as MAC addresses still play an important role in the internet we know. The exercise for IPv6 looks as follows. In the core network emulator, as seen here, we have a network of 4 hosts, 2 routers, and 1 server. In the beginning, the hosts at the bottom left are not configured in any way. Lucky for us, IPv6 supports stateless address auto-configuration, or short, SLAC. During the lab, we go through different steps of SLAC in order to automatically configure both an IPv6 link local and a global address for the hosts. At least for the global address, we learn how to configure the connected router in a way that it announces the necessary information to the hosts. Afterwards, communication between local networks 1 and 2 works nicely. However, for destinations more than 1 hop away, for example from host 1 to server 1, with 2 routers in between, the routers need more information. If we inspect the routing table of one router, which we can do this way, typing the IP -6R. We see that the router already knows how to reach the different subnets in our network. So we have 3 different subnets and a default route in that case, which sends all traffic that is not for one of these 3 directly connected subnets to router 2, which is connected to the last subnet in our network. In this part of the course, we learn how this can actually be configured statically, and in a later part also dynamically using routing protocols. Last but not least, we have a look at fragmentation. When a packet is too large for a certain link, IPv6 has to fragment it into smaller pieces. In the hands-on, we manually decrease the maximum size for packets sent between router 1 and router 2, send large packets from a host to the server, and look how and where fragmentation happens. If this teaser drew your attention, watch out for our ILab X massive open online course starting on edX early 2019.